first term was distribution coefficient and the another term was selectivity. Out of those two terms, let us have a look at the first term, that is distribution coefficient. You are able to see a definition written on the board of distribution coefficient. What is that? It is the ratio of concentration of component C in extract phase to the concentration of component C in raffinate phase. Means, if there would be a mixture of A and C, A is a carrier liquid and C is the desired component to be separated. To this mixture we introduce in a extractor. A mixture of A and C is introduced in the extractor. To extract C from A, we introduce one more component in the extractor, and that is component B, which is the solvent. This solvent fetches component C from A. That is what we have seen in the concept of liquid-liquid extraction. Now in the extractor, it forms a ternary system. A system consisting of three components A, B and C, where A and B both are solvent and C is the solute, the desired component. A is a solvent, but it's a carrier liquid for C when it was initially with A, and C is an internal, which is one more solvent, which is likely to be introduced to fetch C from A. A पासून C ला वेगळं करण्यासाठी आपण टाकलेला जो थर्ड कंपोनेंट आहे B. अल्टिमेटली काय होतं की C जो आहे तो डिस्ट्रीब्यूट होतो A मध्ये आणि B मध्ये, कारण दोघंही त्याच्यासाठी सॉल्व्हेंट आहे. फक्त एवढंच की B आपण जो टाकतोय त्याच्यामध्ये तो जास्त सोल्युबल आहे किंवा त्याची मिक्स होण्याची टेंडन्सी म्हणजे C ची हे जास्त आहे, म्हणून तो A ला सोडतो आणि B मध्ये जास्त मिक्स होतो. पण पूर्णपणे A ला सोडतो असं नाहीये, थोडासा तो A मध्ये राहतो पण जास्त प्रमाणात तो B मध्ये होतो. म्हणजेच काय होतं की C हा डिस्ट्रीब्यूट होतो दोन सॉल्व्हेंट्स मध्ये. त्यापैकी एक सॉल्व्हेंट आहे कॅरियर लिक्विड म्हणजेच A आणि दुसरं लिक्विड आहे एंटेनर म्हणजेच B. सो C solute distributes in two solvents, one carrier liquid A and another internal B. So this distribution has to be expressed in terms of distribution coefficient. When C distributed among those two solvents, solvent A and solvent B, when it goes in solvent A, it will be raffinate phase, and when it goes in solvent B, it will be extract phase. So there must be some concentration of C in raffinate phase, and there must be some concentration of C in extract phase. The ratio of these two would give you the value of distribution coefficient, that is the concentration of component C in extract phase divided by the concentration of component C in raffinate phase. This ratio, WCE, weight fraction of component C, weight fraction of component C in extract phase, and weight fraction of component C in raffinate phase. So this ratio will give you the value of M, where M is distribution coefficient. That's all from distribution coefficient. We have one more term, selectivity. Here is the definition of selectivity. It is the ratio of another ratio. It is the ratio of the ratio. Let us see this ratio first. It is C to A ratio. C to A ratio in extract phase and C to A ratio in raffinate phase. So it is the ratio of the ratio of C to A in extract phase and C to A in raffinate phase. Means it is the ratio of a ratio. Which ratio? C to A ratio. C to A ratio in extract phase and C to A ratio in raffinate phase. So the extract phase and raffinate phase ratio of C to A would give you this ratio, and which is called as selectivity. Mathematically, if it is beta, it is denoted by a Greek letter beta. So beta is equal to, it is the ratio of C to A to C to A in extract and raffinate. So what does this mean? This means it is W WCE upon WAE, means it is the weight fraction of component C, in extract phase divided by weight fraction of component A in extract phase. So this is the ratio of C to A. Ratio of C to A in terms of their weight fractions. What does this mean? Ratio C to A. Ratio C to A means ratio of weight fraction of component C in extract phase to the weight fraction of component A in extract phase. So this is the first ratio in extract phase divided by WCR WAR. This is another C by A ratio, means this ratio in raffinate phase. So it is weight fraction of component C in raffinate phase and weight fraction of component A in raffinate phase. So if we simplify this, this would give you, this is WC extract phase divided by WA extract phase multiplied by, now this denominator would become numerator, so it would become WAR upon WCR. It would go in the multiplication. When it would go in the multiplication, denominator becomes numerator and numerator becomes denominator. So this is a simple mathematics to be learned in standard 8. Don't worry. If you do not know, I have a simplified form for you. So it's WCE divided by WAE into WAR upon WCR. Now, just think a little and tell me whether this selectivity beta can be related with the distribution coefficient. Just concentrate on the formula of M, which we have seen earlier, and concentrate on the formula of beta, that is selectivity, this formula. I will give you 5 minutes. Just think over it. hope you have done it correctly. Just verify, just validate whatever you have found with my calculations. This ratio can be rearranged as WCE divided by WCR into WAR divided by WAE. Now concentrate on the first part of this expression of this part. What is this part? This part is weight fraction of component C in extract phase and weight fraction of component C in raffinate phase. So this is extract phase concentration of component C, and this is raffinate phase composition of component C. So it is a ratio of component C concentration in extract phase to raffinate phase. What is this? This is M. What is that? This is M. M means diffusivity. So in turn, you can write M into WAR divided by WAE. So we got the new definition of selectivity now. What is selectivity? According to this relation, selectivity it is diffusivity times the ratio of component A in raffinate phase and extract phase. What is that? It is means what? Selectivity. Beta is distribution coefficient times, means distribution coefficient multiplied by the ratio of raffinate phase concentration of component A to the extract phase composition of component A. Component A is a carrier liquid for C. So that is the another definition of selectivity. The first definition is elaborately given, written on the board in front of you, and the second definition is in terms of diffusion coefficient, that is M. It is M times the ratio of concentration of A in raffinate phase to extract phase. What is the significance of the term selectivity in liquid-liquid extraction? Selectivity is one of the criteria to select a solvent for liquid-liquid extraction to have an efficient separation of C from A. The significance of selectivity, that is the role of selectivity in liquid-liquid extraction. It serves two purposes. The first purpose is the separation factor. Separation factor which is responsible for an ease separation of C and A. C to be separated from A. So it's a separation factor. It's a measure of a separation factor. And the second role, which is analogous to the first one, means which is the another form of the separation factor, the definition of separation factor. It is the ability of the solvent B. Of what? What is the ability? The ability of solvent B to dissolve component C. To dissolve component C, but how? Preferentially with respect to component A. Component A पेक्षा component A पेक्षा component B component C ला जास्त डिसॉल्व करण्याची क्षमता ठेवणे, ही ॲबिलिटी जी असते ती ॲबिलिटी आपल्याला सिलेक्टिव्हिटी सांगते. it is written, the ability of solvent B to dissolve C in preference to A. A च्या comparison ला B नी C ला जास्त dissolve करणार. When a mixture of A and C is treated with B, where to treat? Of course, in extraction column, in an extractor. So its ability of B to dissolve C preferentially with respect to A when the mixture of C and A come in contact with component B, where component B acts as an entrainer or solvent for